Alright, we're going to see a demonstration of a coalescing air and dirt separator, and this is a demonstration of a typical closed loop system. When we get to the dirt part, this will also apply to any open, like a cooling tower application as well. Now right now the system is running. See by your little indicator there, pump is circulating. We do have it running in bypass right now. This is our air and dirt separator. We have a little sight glass in the top for you to visually see the bubbles coming out, and this is our makeup water expansion tank. One of the things I'm going to do right now is I'm going to pump in some air. And what we're simulating is a couple things, whether it's a change in temperature and pressure that's making the air come out of the solution, the dissolved air come out in the solution, whether it was just some routine maintenance where there's some air that got in the system that way and filling up the pipes again. What we want to show you here is that, I pumped in a lot of air and this system is still circulating right now. So you may think, well, I don't really have any problems with air. My facility is heating or it's cooling fine. Nobody's complaining. The system is working. You still may have air in there, and you very likely will. It's just from an efficiency standpoint, you may not be reaching the peak system that it was designed for. But when I put some air here, the first thing that you hear is the pump cavitating. So first and foremost, you want to get all the air out just to protect your equipment. Pump seals and bearings will break down, yes, but our customers say, hey, I'm having to replace these things a lot sooner than I should, and when we investigate, usually air is a big factor in that. It just shortens the life of them. The other reason why you want to get the air out of your system, besides just protecting your equipment, is air is a really good insulator. You see all these bubbles circulating through here. Anywhere in your systems that the BTUs are being exchanged, so the steam converters or chiller evaporator tubes or any kind of air handling unit coil, all those places, if you have air in there, it's slowing the heat transfer down. So it's working, but it could be working a lot faster and therefore saving you energy by just simple equipment not needing to run as often. And then there's also, potentially you get better deltas at coils and satisfies customers, but you also don't get the noise that you would too, which is something you can't really have in a healthcare environment. And then, getting back to equipment and energy, there's a lot of wire to water energy being wasted right now with this pump, because what's happening is it's trying to squeeze those air bubbles. Air is compressible, water is not, and it's referring back to that slide I showed you in the beginning about how just a couple percentages of entrained air can reduce the pump efficiencies. You're actually going to see the water, it's going pretty fast now, it's going to go even faster once I start taking the air out of here, because the pump is not having that resistance of the air on the impellers anymore. So right now it's like you got a foot on the gas and you're lightly tapping the brake at the same time. So this is how it works. Right now we're running it through the spiral vent, and what we're doing is we're bringing in the water, we're slowing it down. That's why the vessel's tall the way in that shape, and then we bring it back through again really quick. You can see just little bubbles. The big ones go right to the top. I'll put some more air in there again so you can see big slugs of air just naturally rise because it's so calm in there. The other equation with just slowing the water down is filling it up full of this media, which takes out the turbulence in there, and that's what makes things calm and these little bubbles are able to rise. The other part of its engineering is to attract air bubbles, which basically that's what the coalescing term comes from. They adhere to this mesh and other bubbles collide into those, and once they become big enough, their buoyancy just carries them up to the top. And the way that these are operating is we're taking out all that free air, the big masses of air is getting removed through this. We're also getting that entrained air, which is those smaller bubbles. These little tiny ones, it's removing all those as well. And at the same time as it's removing bubbles, we actually have a small pressure drop by design in there to get the as much as the dissolved air as Mother Nature will allow us to. And that's, you know, breaking the air out of solution, so to speak, and it's either got something to cling to or eventually it hits the mesh and vents out at that point. And then what we're doing is we're stopping the corrosion from happening. And this is probably the easiest indication that you have air in your systems is dirty water. And we see all different kinds of shades of browns and blacks out there, but you know, the water was clear. What happened? And actually, I want to show you one other trick too while we're watching the dirt, which this is simulated dirt from it's zeolite from a water softener. It's a really good imitation of what we see out there, the rust, typical rust particles. Now dirt too is a very good insulator, just like the air, so affecting your heat transfer and your efficiencies. It definitely will trash equipment pretty quick. But as it's getting the air, just pay attention to this large air bubble in here too at the same time. Alright, so running it through, you see the air bubbles rising, the dirt particles are falling. And you see the air bubbles, pretty much just a little tiny bubble now. Most of it's been sucked out because of the water becoming absorbative. And that's how we're stopping the no heat calls. But you see the water's getting semi-clear, a little more in there. You know, this isn't a filter, it's not a one-time pass. Like, even though we are filtering the water, as a separator, it needs to see it repeatedly. And if it's denser than water, it will fall to the bottom of that vessel. Now, we get asked a lot, do these things clog? And the answer is no. The way that the mesh is designed not to clog, but also the way the vessel is constructed, as it's pulling debris, it can only rise up to the bottom of the pipe. And then it's just going to continue to circulate whatever material is left in there. It'll still remove air, it just loses its ability for any dirt particles to fall until somebody is able to purge the vessel. And that's it, it just stays in there. Even for, we've seen them go for months at a time where there's been a bunch of crud in there, and it just, the system pressure just flushes it right out. After 100 passes, it's down in the 30 micron range. These do have the capability to get down to 5 microns. That's the best that we're told, and for most applications that's more than enough. But that's it. You see the water's clean. It's clear of bubbles, and it's quiet, and the pump is still running. That's how you want your systems to be. That's what makes them efficient. And that's what makes happy occupants and saves energy in the process.